Hello, hello, hello. We're excited to have you here and want to welcome you to Flatiron School's Exploring System Design. My name is Corey Mickelson, and I am the event coordinator here with Flatiron School. A big part of my job is hosting free introductory workshops like today's event to give you all the opportunity to meet some of our team and get a better feel of the Flatiron School experience. A quick reminder, we will be using the chat as our main source of communication, so make sure you change that little blue button from host and panelist to everyone so we can all chat together. We will also be holding all of our questions directly related to the event until the last 15 minutes. Feel free to drop questions in the chat as they come up, and we'll save them and address them during the Q&A portion. Without further ado, I'd like to introduce our guest for today. Zach Little is here representing our admissions team. Go ahead and say hi.
Hey guys, I'm your admissions lead. So as you get through this, admissions questions, feel free to drop in the chat.
And then we have Alvi is here representing our software engineering team. Go ahead and take it away, Alvi.
Thanks, Corey. Hi, everyone. I'm Alvi, and I work on the software engineering curriculum team. And let me start sharing first, and I'll briefly talk about what I'll be covering today. So hopefully everyone can see my screen. If not, feel free to let Corey know in the chat. Also keep the chat open so I can see the questions when we get to that. All right, so the first thing is what we'll be doing today, right? So my goal for today is to give you the context behind system design. So if you have done some research into software engineering, or like what sort of skills are expected of software engineers, you might have come across terms like system design, right? So my goal is to give you some context around what that means, what the interviews look like for system design, and how to prep for them. I'll also briefly touch upon like when you might want to start learning about system design, but that's for later, right? And if you have any questions while I'm going through this, feel free to ask in the chat, and then I'll get back to you at the end of the session, where we'll have a Q&A session. And also, if the question is specific to a certain slide, feel free to note the slide as well, right? So without further ado, let's get started. So we'll start by discussing what system design is and some core concepts that might be helpful as you dive deeper into this topic. Then I'll talk about how the interviews are like and how it differs from other types of interviews you might encounter. And then finally, I'll talk about a study guide that you can use to learn more about system design and prep for early to mid-level interviews, right? So system design. So even before I talk about what systems are, I'm going to talk briefly about some common terms. All of you might be familiar with it already, but I just want to make sure everyone's on the same page. So we'll get started with that. So whenever you hear the term computer, right, it can mean different things to different people. But in the case of system design, what we primarily care about are these three components inside the computer. I've added the network card here as well, because if you're going to be designing systems, they will communicate with each other, right? So you'll have a bunch of systems that will communicate with each other, and they have to do that through a network, which is why this thing here is in this box. But when you hear terms like server, client, load balancer, databases, and all that, all those fancy terms, at the core of it, all of them will have a CPU, a RAM, and some sort of storage, right? So the CPU is where the computer does its processing or calculations. So anytime you ask the computer to compute something, so for example, if you ask it to do some addition, the actual processing and the calculations happen in this component, the CPU, or the central processing unit. And then you have your RAM here, right? So the RAM is where you store temporary data, right? So whenever you run an application, this is where the application code runs. So whenever you start a web browser or a video player or a game, it will run its code from this area, right? And it's called random access memory. You might see this being referred to as just memory in some of the guides and books you read. So that's something to keep in mind as well. And then finally, you have storage. So RAM is for temporary storage of information. The storage thing here, this could be a hard drive, an SSD, a thumb drive, etc., right? Or a memory card. It could be a lot of stuff. But the main purpose is to store data permanently. So if you want to store information for later access, this is where you would store. So a RAM clears its data whenever the computer closes, right? So whenever you shut down a computer, the RAM gets cleared. So any data stored on there is lost. When you close an application, generally it will also clear all of its data from the RAM as well. So if you want to save some information, you would have to use a storage, right? The reason why I bring this up is when we talk about servers, we'll see lots of different types of servers. And depending on their use case, they might have a bias towards one of these components. So for example, if you have a database server, the storage component will be more highly weighted, right? So you'll have more storage in a database server than you would have, for example, in a web application server, right? So that's just something to keep in mind. The next important thing to know is a network, right? So as I said before, all these terms, servers, load balancers, clients, caching, and all that, all of those services are just computers. So a network is a connection between one or more computers, okay? So having a network card allows a computer to tap into certain types of networks, right? So for example, if you have Wi-Fi in your home, your device may have a Wi-Fi module that connects through the Wi-Fi, right? It doesn't have to be cable in this day and age, but that's how it works. This map here actually shows the physical cables that connect different computers across continents, right? These are called submarine cables. And this is pretty interesting. I have put some links towards the end of the slide where you can go to this map and check it out. It's interactive, so you can zoom in and see what sort of connections there are. All right. So for our purposes, a network is a collection of computers that can communicate with each other. All right. This could be through physical means like cables, or it could be wirelessly through your mobile data or your Wi-Fi data, right? Now, this is the standard model you will see when you start studying web applications, right? So just to clarify some terms, client refers to things like your laptop. It could refer to your phone. It could be any smart device. So like it could be a smartwatch as well, right? So anything that sends a request to a server, right? So for example, if you're using a web browser, right, and you go to google.com, your browser in this case is acting as the client. Google.com has the server, right? So your request goes to google.com, and then google.com sends you back the page that you want to display to your user, right? If you use other applications where they have persistent data, for example, Instagram, you go to your app. So in this case, the client would be the Instagram app. It sends a request to your server, right, which is instagram.com. And then instagram.com gets the images that are stored in the database related to your followers or people you are following, right, accounts you follow. So it sends a request to the database, give me back the images. So the database server, or database in this case, gives the server the response, and then the server sends it back to the client, which is the Instagram app in this case. So now you can finally view the images on your app, right, which is the Instagram app, okay? So this is the general model that you might see when studying software development. And just as a quick note, this model is pretty robust, and with modern tools and services, this can serve like millions of users, right? So if you're just getting started with an idea, don't worry too much about system design, right? Don't worry too much about scaling and all that. It's completely fine to start simple and then move to a different architecture or system as your user base grows. All right. So if you look at older versions of popular websites, you'll see that they didn't have all the features that they have right now. Okay. So it's better to start small, test out your idea, iterate on it, and then scale, right? Instead of scaling from the start, unless you can guarantee you'll have like hundreds of millions of users from the first day, which is realistic, right? So what are the problems that you might run into if you have just a single server? All right. So think a bit about this. So you have a client, so you have a web browser, and it's not just one client, right? Multiple people can access the website and then send a request to your server. So for example, if I'm sending a request to google.com, it's not just me who's using the website, right? There are hundreds of millions of people who use google.com every day. So what are the problems that might come up if a single server is receiving lots and lots of requests, right? So there are some problems with that. First is the performance limit, right? Now, under all of that, right, the server is just a CPU, RAM, and storage. And all of these have limits on how much they can perform, right? So the CPU has a limit to how much calculation it can do. The RAM has a limit to how much information it can store. The storage also has a limit on how much stuff it can store, right? So if you have one machine, then there's an upper bound or a limit that you can hit, okay? And then the components are pretty expensive to upgrade, right? So let's say you are receiving more and more requests daily, right? And you need to upgrade your server. So you upgrade your CPU, upgrade your RAM. So CPUs are expensive, right? So if you keep upgrading CPUs, it's going to cost a lot. And then the cost doesn't scale linearly, right? So if you want to go to a higher model of CPU, sometimes it can cost like a lot more than the lower end ones, okay? So server CPUs, they can have, they can cost thousands of dollars for one CPU, right? And then you have scalability limit. What do I mean by this? It means if your user request suddenly grows, right, your server wouldn't be able to handle it. So for example, let's take a news site, for example, right? News sites get a steady amount of traffic, but if a certain event happens, right? So for example, there's maybe, I don't know, an alert of some sorts. Like we have air quality alert in New York at the moment. So if you have something like that, more people might come to the news website to check what's happening, right? So suddenly you have an influx of user. But because you have a limited amount of CPU and RAM, you may not be able to serve everyone who visits the website, right? So scalability means being able to scale with the amount of requests that your server receives, okay? And then no redundancy. What this means is if that one server goes down, your site completely shuts down, right? Basically, there's no backups, okay? And finally, low availability. What this means is availability refers to the amount of time a service is available over a certain period of time. So for example, if a service is available 90% of the time in a given month, that means for 10% of the time it's down, like people can't access it. So if you have one server, there might be several reasons why it may be down, right? You may be upgrading components, so you have to shut it down and then restart it. There may be power outages, so you'd have to shut down and then come up or like restart the server again, right? So those are some of the issues that come up if you just have one machine serving your users. So how do you solve that, right? You solve that by adding more computers together or servers together and then making them connected to a network. So what happens is instead of sending a request to a single server, the requests from the users can be distributed across different servers, right? So for example, if I go back here, so instead of having just one server, right, you could have another server here. You could have one here as well, and so on. So your different clients might send it here or here, or to this one, right? So that's how you might solve some of the issues with a single machine setup. And when you have multiple servers connected through a network serving requests, that's a distributed system, right? And it does solve most of these issues here, right? But it also introduces certain issues of its own, which we'll talk about in a bit. But before that, this is the structure of a large-scale application. So Slack is a messaging service, workplace messaging service, if you're not familiar with it. So this is the setup for sending or receiving a Slack message, right? If you use other services, so like if you use Messenger chat, Instagram chat, LinkedIn chat, or whatever services you use, they also may have a similar setup, right? And you can see there are all these different names here, like you have web app, you have admin server, you have channel server, and then you have gateway server and all this stuff. And then you have the clients here. In this case, they're displaying mobiles, right? So as you can see, the distributed service does solve some of the problems for single machines that we saw. So because you have multiple servers, you can add more servers as needed. So if you have more users, you can add more servers, right? Similarly, if one of the servers just stops working, the entire system won't fail, right? If one of these go down, you still have these available, right? So it adds redundancy to your system. That way it doesn't completely shut off in case of an emergency, right? And then you have gateway servers and edge regions as well. So basically what this means is if you have a very popular application, it may be used by people across the world. If that's the case, you want the system to be available closer to the user, right? So you might have multiple servers in different regions or countries to serve, okay? So those are just some of the considerations. So fallacies of distributed systems. What this means is when people start working with systems like these, they make certain assumptions that are not true, all right? So that's why these are called fallacies. So let's go through some of these quickly and then see what the issues are, okay? So the network is reliable. So this is a false assumption because no network is 100% reliable, right? In fact, just about an hour ago, my network went down and it seems like they have people here working on the poles right now just to fix the network. So you can never assume that a network is reliable, right? Latency is 0. Latency means the amount of time it takes data to go from one place to another, right? So for example, if you send a request to google.com, it might take 50 milliseconds for the response to go to the server and then come back to you, right? So the problem with this assumption is that all of the information we send across networks travel through physical systems, right? And it's not physically possible for a thing to go from one place to another instantaneously, right? So the assumption that data can go from one place to another instantaneously is false. And then you have bandwidth is infinite. So bandwidth refers to the amount of data you can send within the latency time. So for example, I said the 50 millisecond is the latency to send the information from your website or like your computer to Google's server, right? It takes 50 milliseconds to go to the server. But how much data can you transfer within that window, right? How much data can you transfer within that 50 millisecond? Okay. So you might also see this as your internet speed. So if you have seen Mbps, Gbps, terms like that, it refers to the amount of bandwidth you have. So if you have a 300 Mbps connection, that means your network can send 300 megabits of connection over 1 second, right? And again, this is not infinite, right? Because if we were able to send unlimited amount of data, that would be really amazing, but that's not the case. And then in the modern world, we have tons of data going over channels or networks, right? So if you have a video, that takes up more information, and then we have increasingly better video quality over time, right? So we have 4K now, which takes up a lot of bandwidth when the data is being transferred. So that's also a wrong assumption that bandwidth is infinite. The network is secure. So when you send a request, the request might be sent over lots of different systems across different regions, across different countries, and so on, right? So it's highly likely that some of those networks that your request goes through may not be secure, right? So you can never assume that a network is fully secure, which is why when you design systems, you have to take security into consideration. Topology doesn't change. So topology in this case means the structure of your system, right? So for example, if you have multiple servers, right? So you have 1, 2, maybe 3 servers for your website, right? So you have 3 servers that are connected to each other. Oops. They're connected to each other. Okay. So topology refers to the structure here. The topology here right now is 3 servers, but one of them might go down, and so the topology changes, right? Similarly, from the client side, if you have clients, right? Let's say you have a phone here, right? So there might be three users trying to access your service, right? So one of them has finished whatever they were doing on your service. Maybe they scrolled through their feed and now they're done. So they would stop accessing your server, right? So the client topology also changed, which is what this references. Okay. So that's what topology means. There is one administrator. Again, when you build large-scale systems, you'll be working with lots of different teams. You might also use third-party services, right? So you won't be fully in charge of everything, okay? The bigger the website, the bigger the service, the higher the chances that there are more than one administrator who controls all the permissions, right? So when we design systems, we have to take into consideration that we may not have certain permissions when we are making networks through other people's services, right? Transport cost is 0. What this means is whenever we send data, right, there's 2 types of cost. The first is computation cost. So whenever you send data over network, your data needs to be secured, right? So there's some sort of encryption that might happen, which takes up time. your data also may need to be converted to other forms before sending it over to the network. Okay, so there's some computation cost with sending data. The second cost is monetary cost. If you're using if you're using other people's services, there's a certain amount of cost that's associated with the transfer, right? So you can't send data for free, right? Someone down the chain will have to pay, right? You might have free services, right? They provide some level of free service, but someone is incurring those costs for you, okay? And then finally, the network is homogeneous. What this means is all the computers are of the same type in a network, right? So as we have seen before, that's not the case, right? Even just the clients can be of various types. They could be using different browsers. They could be using different phones, different types of computers, different types of devices, and so on. The servers themselves are also the same. You might have different types of servers depending on what their final goal is. So for example, as I said before, you have database servers whose primary job is to store and serve data, right? Whereas you might have web applications whose primary job is to compute something, right? So for example, if you go to linkedin.com and then you sort your feed according to top news or new articles, right? So somewhere along the network, the web application or the web server will be doing those computations, right? So these are the fallacies of distributed systems. I provided a link in the resources where you can go and check out a bit more information and explanations on these fallacies, right? So whenever we're designing a distributed system, we have to be aware that the network is unreliable, latency is never zero, we have limited bandwidth, the network is not secure, the topology might change, that is, our servers can go down at any time, right? So we have to account for that. There might be multiple administrators, there's always cost associated with transfer, and then we might have multiple types of devices on a network, right? So with all that said, what does system design actually mean, right? So system design is basically the process of designing a software system which involves making high-level decisions, right? And this keyword here, high-level decisions, is important, right? Because these systems are really, really complex, right? It's not possible for one single person to know everything there is to know about each of these systems, right? So as you work in the industry, you'll develop expertise around certain parts of a system, right? So when you're talking about system design during interviews, you'll primarily be talking at a very high level, right? High-level decisions and choices regarding the structure, components, interactions, and behavior of the system, right? So we'll talk briefly about what these mean in a second, but then this line is also really important. Meet specific requirements and achieve desired functionalities, all right? So depending on the kind of app you're developing, you'll have a specific set of requirements. So for example, if you're asked to design something like Uber, right? Specific requirements might be users are able to call for a ride, or a driver is able to accept a ride request. A user is able to track their location as they do the ride, and so on, right? So those are some requirements that may be discussed. Okay. So with all that said, let's talk about how these interviews are structured. Okay. So the very first thing I'd like to point out is how coding focused interviews are different from system design interviews. All right. So when you're doing coding interviews, they give you very specific problems. All right. They give you inputs, they give you expected outputs, your job is to figure out how to write an algorithm that goes from the input to the output, right? So these are very well-defined problems, which usually have an optimal solution or multiple optimal solutions, right? So for coding interviews, you'll be given a problem, you'll have to come up with a solution and then implement the solution. And then usually you'll discuss some optimization with your interviewer, and that's that. For system design interviews, that's not the case. The first difference is when you're given a requirement, the requirement is very vague, right? So for example, they might tell you design Uber, right? Now, so both coding interviews and system design interviews are about an hour to an hour and a half long, right? It's not possible for anyone to design Uber in one hour, right? So what you have to do is get clarification on what part of the system they want you to focus on. Is there any specific area they would like to highlight more than the other? So for example, maybe they're just interested in the system that determines if a ride is available, right? So they have really broad scope, and then your job as the candidate is to make sure to ask clarifying questions, right? And then the most important thing here is this. It's a collaborative process, right? The entire point of doing system design interviews is for the interviewer to get a sense of how the candidate thinks and communicates, right? Because when you work on a software engineering team, you'll have to work on different kinds of systems, you'll have to make decisions, you'll have to work with multiple people on the team and so on, right? So you need to be able to justify your decisions as you design these systems, right? It's a very collaborative process, unlike coding interviews where there's some back and forth with the interviewer, but you are the one who's primarily talking about what you're thinking, right? Whereas in the system design interviews, the interviewer might ask you clarifications as you're describing your thought process or your decisions. Calculations. What this means is if they ask you to design a system, let's say YouTube, for example, you have to make some calculations about how many requests your service might get in a given day, in a given month, or any other specific time period, right? So like, for example, you would ask the interviewer how many users you expect for this system. They might say 50, 100 million, and then you have to make an educated guess on how many requests you might get from those 100 million users in a given time period, right? You don't worry like how to do these calculations. I've provided resources that go into more detail about these things, right? Establishes the scope of the design. Again, this is about clarifying what specific part of the bigger system they want you to focus on, right? So for example, if it's YouTube, maybe they want you to focus on just counting the number of likes a video has, right? It might seem simple, but there's a lot of complications involved, even with just that one feature. Or they might ask you to design the notification service for a certain system, right? Defines a data model. So any application you use have some sort of data associated with it. For example, if you use LinkedIn, you'll have some data on the types of users, right? You might have data around the posts. You might have data around the job listings, okay? So your job might be to define what those data would look like in databases, right? For entry-level interviews, you can sometimes get away without defining a data model, but it's probably a good idea to at least define some data, or like the important data that you'll be storing in the system. and then you propose a high level design, right? What this means is there are some general system design blocks, if you will, right? Think of them as Lego blocks, right? So you have the web server, you have the database, you have cache, and so on, right? So your job will be to like figure out how these pieces fit into this specific system design problem, right? Again, there are examples of that in the resources I've provided. Defines the APIs for the system. So this defines or lays out how your servers will communicate with each other, right? So for example, one server might have a function that calls another server to get the number of users who are logged in, right? Or in this case, take the Uber example, right? Call a ride, right? So call a ride, it might take in your current location and your destination, right? And then based on that, it will do some calculation on where the driver might be, okay? So once you have done all of these, finally, you and your interviewer might discuss details, trade-offs, and extensions to the problem, right? So as you design the system, your interviewer might ask questions. So like during any of these steps listed here, they might also ask you clarifying questions, right? But at the end, they'll definitely discuss like what the issues are with the system you've designed, because no matter how well you design something, there are always trade-offs, right? So you as the interviewer will have to identify what the trade-offs were, where you could potentially improve, how you would improve things if you had more time, and so on and so forth, right? So that's the general process of how a system design interview goes. So this step and this step aren't usually asked for entry-level roles, right? But again, it might be a good idea to still use those because it shows that you have the necessary skills for designing systems, right? Or at least you have the framework to think about the different things that go into designing a system, right? Because as a candidate, your goal is to signal to the interviewer that you are knowledgeable about these things and that you can solve problems as they come up, right? Which is why it's important to have a framework for approaching these sort of problems and then following them through. So these are some things that the interviewers are looking for. Since we are a bit short on time, I'm not going to go too much into them, but these are the things that the interviewers are looking for, right? So the study guide. So all of the things listed here are free. I wanted to make a study guide that doesn't require you to spend money, so you can learn the fundamentals without like buying courses or books, right? And then once you have that basic foundation, you can decide what sort of books you want, what level you're interviewing for, and then get specific types of books. With that said, I do have book recommendations in my resources, but everything on this slide is free, right? So the purpose of these 3 videos is to get you accustomed to the basics or the lingo of the system design world, right? Because if you directly jump into a guide without like having a higher level overview, it might confuse you, right? Which is why if you go through these 3 videos before going through any of the guides, it'll give you at least some foundation to build off of, right? And then this guide here, a senior engineer's guide to system design interview. Don't get scared off by the word senior here, right? From what I've read in this guide, it's not really geared towards like very high level interviews, right? The language is fairly approachable. They use analogies. So even if you I think you'll be able to follow along even if you don't know how to code properly yet, right? It's fairly simple language. So this should give you an idea of the kinds of things that are involved in the interview. And especially in part one, they do a really good job of setting the context for interviews, right? So all of the things I've been saying so far, they explain those further, and then they talk about what the goal is and how candidates are expected to behave during those interviews. And then system design primer, this basically expands on certain parts of this initial guide, all right? I would highly recommend that you read both of these. But if you go through just this, you should be ready to start watching system design videos or going through books, okay? So the first part of the study guide is to learn the fundamentals to set a solid foundation. And then you have to start practicing, right? Again, this is free, but these are books. So these cost money, but if you have a library nearby, you may be able to get these for free as well, just so you can check them out before purchasing them. Or I think Amazon has previews for these, so you can also check that out. But basically, these have lots of case studies of how to design systems. So like they walk you through the framework as well as different types of systems that you can design using those frameworks, right? But before that, watch this video first just to get a sense of how you might design a system. The guides I mentioned earlier also have videos as well, so definitely go through those. But before you start practicing or solving problems on your own, make sure to at least watch this video, okay? And then we have the Q&A session, right? Let me see what sort of questions we got here.
Thank you,
Okay.
Albie.
Yeah, I'm just looking at the Q&A. Okay, so there's a great question here. How deep should one prepare for system design if asked for in product or program manager interviews? So from what I've seen, product and program managers are also asked system design questions from time to time, but they aren't expected to do deep dives, right? So they probably won't be asked to design the data model, the API, or talk about the algorithms you might use for certain parts of the system, right? Another thing to note is system design interviews are mostly done by mid to large corporations, right? Recently, smaller companies have also started asking these questions, but the scope is a lot smaller, right? So when I say mid to large corporations, I mean companies that have like engineering teams in the hundreds, for example, right? So yeah, those are the kinds of companies that ask the questions. All right. Is a systems architect the same as system designer? So in software engineering, so the person who designs the system may not necessarily be called the system architect or system designer, right? So senior software engineers, staff engineers, principal software engineers, they also are involved in the process. I haven't seen system designer as a role. I have seen system architects, right? But generally, if you are a mid to senior level engineer, you would be expected to get involved in the system design process. Great question. Any other questions? I know we're a bit short on time, but any other questions before I talk a little bit about the resources? All right, great. So for the resources, on the first slide, from this point up to this point, these are all resources from the study guide section, all right? This is the new edition, Understanding Distributed Systems. I highly recommend this because it will give you general overviews of considerations for distributed systems. And the language is very beginner friendly, right? And it has some great diagrams as well. So after you have finished going through the learn system design fundamentals slide, or these things here, highly recommend that you start this book, right? It's not that long. It's like 250 pages or so, right? And includes lots of diagrams. So actually it's shorter, but it's a really great book. And then you have these engineering blogs. Again, once you have learned about the fundamentals, you'll be ready to start reading engineering blogs. So engineering blogs are where companies post their solutions to problems they've encountered in production, right? And these can range from a little bit of detail to very detailed, right? Sometimes they might put out papers as well. These are some great blogs that you can go through. These are some selected ones. The full list is here. So if there's a particular company you want to apply to, you can go to their specific blog and then see what sort of problems they're working on. And maybe you can discuss some of those during your interviews. The first one here, high scalability, is more general. They discuss like high-level designs for different types of services. And then finally, these are some resources that will help you visualize the network maps that I showed earlier, and then some articles that might be worth reading. Like this one here, Fallacies of Distributed Systems Explained, does a really great job of explaining the fallacies, like why they're fallacies in the first place. And then this one is just the link to the Slack architecture I showed you, right? So just to reiterate, focus on the fundamentals first. It should take you about 5 to 7 days to get through the foundations, or the foundational videos and guides that I listed. Maybe 2 weeks if you're doing it part-time. And then you will be ready to start reading most of the books and start watching system design videos, right? So with that said, thanks everyone for joining us today and for asking all the great questions. If you have any questions about admission, I think Zach and Corey will be able to take them now.
Thank you so much, Alvi. That was incredible. Well, if we don't have any questions, we'll go ahead and wrap up. Thank you, everybody, for joining us today. And thank you, Alvi and Zach, for coming in. Alvi for a great presentation, Zach for a little bit of support here in the chat section. And we hope to see you at another event soon. Have a great day.